Hello everyone. Now these three categories, you see lots of methods proposed in last 2-3 years. We discussed knowledge editor from global optimization. So now we will discuss ROAM, locating and editing factual associations in GPT. This is a very famous paper by MIT and people from other universities. So in this paper, now how this ROAM paper is different from Grace and knowledge editor. So here this is a new paradigm, which is local editing, right? So here they said that I will first identify the location which needs to be updated, and then I will update that location. Okay. So before ROAM, let us understand the transformer model once again, and I will discuss this in a different lecture when I talk about the interpretability. But this is a perspective of transformer which says that this is called the residual stream perspective of transformer, residual stream view of transformer. If you remember transformer architecture, there are these inputs, layers, right? Inputs are fed through layers, pass through layers, and then you get some output, right? So in this perspective, every input token has an associated residual stream. Input X has a stream. The stream is nothing but, you can think of it as a pipeline, right? So every input has a corresponding pipeline, and when this input is passed through layers, things get added to the pipeline, right? What are the things which get added? The feed forward output and the attention output. So as if there's a stream going on and things get added to the stream. So this is a localized view, because now you can dissect all these streams separately, and you can basically make operations on every stream separately. Okay, so these are the streams. So stream 1, let's say stream 2, stream 3, this is x1, this is x2, this is x3, right? Feed forward, you remember feed forward operation is what? Feed forward operation is a point-wise, position-wise feed forward operation. So this feed forward operation is independent of other streams. But attention is something which is dependent on other streams, right? So you can think of these streams, these residual streams corresponding to different inputs, and there is another stream called attention which cuts across all the streams. Okay, so this is attention. In fact, if you do some sort of bifurcation, more segregation, you see that this residual stream is nothing but at every layer L, let's say HL, the output of the layer L is nothing but HL minus 1's output plus attention at L plus multi-layer perceptrons output at L. Okay, if you are not very convinced with this, I just request you to just bear with me here. Just assume that it happens, and then in the later classes I'll tell you why this is correct. Okay, so now we are viewing transformer as residual streams. Okay, so far we viewed also all the figures that I displayed where transformers were viewed as a vertical pillar. Now you rotate it clockwise. Assume that this is a horizontal pillar where there are different residual streams. This is one residual stream, this is another residual stream, and so on and so forth, right? This is the input, the space station is blah blah blah, right? These are input embeddings. Okay, this is the first layer, this is the second layer, third layer, and so on. The first layer, this is the hidden state, right? And then you basically do, so this square red block is the attention, right? This green block, this one is multi-layer perceptron, this MLP, and then so attention and MLP will give you the next hidden state, and so on and so forth, right? If you look at it very carefully, these red blocks are connected. You see, red blocks are connected, right? Look at these two red blocks, these are connected like this, and like this, because this is attention. okay, where the green blocks are not connected, independent. Okay, so this is the view of a transformer. Now what they did something called causal tracing, right? What is causal tracing? Causal tracing means, let's say the model produced a wrong output. You basically you start from the last output to the last layer and trace back to the previous layers to identify which components are responsible for this error. Okay, backward direction. This is called causal tracing. We'll discuss the causal tracing more. So you see here, every hidden state is a combination of the previous hidden state, the attention at that layer, and what is M? M is the multi-layer perceptron, right? Again, pay attention to the notation. The subscript, the superscript L indicates the layer, and the subscript I indicates the token. Okay. So the entire transformer, you can think of it as a matrix where in this view columns are the layers, okay, rows are the tokens, right? So Lth layer ith token, L plus 1th layer jth token, right? All right. Now attention, as I mentioned, attention is essentially an operation which is parameterized by hidden states of all the tokens in the previous layers. So AIL is a function of H L minus 1 1, H L minus 1 2, and so on and so forth. Now this is important. Okay, I told in the Grace lecture that the MLP, the multi-layer perceptron, is a combination of two feed forward kind of layers, right? So the first feed forward layer is called WLFC. L is the Lth layer, right? So fan out, then fan in, right? So this is up projection. Up projection is parameterized by WLFC, and down projection is parameterized by W sub project. Okay, and what are the things happening here? Tell me. So the input to the MLP is what? Input to the MLP is the output of the attention, right? So the attention is this AIL. Please look at the notation again. AIL is the attention at that layer, right? HIL minus 1 is the hidden state of the previous layer, right? This plus this, okay? This will be passed through a non-linearity, and this will be fed to the multi-layer perceptron, right? Now this MLP, now this will be fed to this parameter, right? W sub FC, and it will be multiplied, right? Then again another non-linearity, right? This will be fed to another layer which is W project, right? And it will produce the output of the MLP, which is M sub I at the Lth layer. Clear? So here I introduce a concept of knowledge neuron. Knowledge, now these are very fancy terms, by the way, okay, but these are very simple. So knowledge neuron. What is knowledge neuron? So in one of the papers, they said that this multi-layer perceptron is responsible for storing knowledge, right? And you can think of this multi-layer perceptron as a key value association memory. What does it mean? They said that the output that you obtained here, the output that you obtained at the middle of the feed forward network, the middle of the multi-layer perceptron, right? This output is the key at the middle, okay? And when you multiply this key with W project, it will produce the value. So the W project acts as an associative memory, and this is kind of an embedding, right? Lookup table. You have this key, you multiply this with this W, and it will return V. Okay, key value association. So again, this knowledge neuron is one of the concepts that they used here to describe their model. All right, so in this architecture, the input is the space station is blah blah blah, is in downtown dash, and the output, and this is an autoregressive model, decoder model. The last layer's output is important. The last layer's output is Seattle. Okay, this is the correct output. Now what you do? So now you run this transformer multiple times. So and you call this different runs and different versions of the model. In one version, which is called the clear run, in clean or clean run, whatever, clean run, in clean run, you feed the input and you get the output as Seattle, which is correct. Everything is clean, right? And you measure the probability PR. What is PR? PR is the probability of returning the expected output. Here the expected output is Seattle. Okay. Now what you do? You run a corrupted output. You run a corrupted model. What is this corrupted model? In the corrupted model, you corrupt the input, embeddings of the input. You see this yellow block, right? This yellow block is the original embedding of the input plus some sort of error, noise, and this noise is sampled from a Gaussian, right? So you corrupt the output, so you corrupt the input, right? And you then run the model. So the output that you obtain at the end may not be Seattle, maybe something else, right? And that is the probability. So the probability of returning, now in this corrupted model, what is the probability of returning the output Seattle? This will definitely be lesser than or equal to the previous one in the corrupted run, right? Now when they corrupt this network, they only corrupt the subject of the input. What is the subject? The space station is located in the downtown Seattle. The subject is the space station. Okay, they only corrupted the subject. You see, the other embeddings are not corrupted. Only this many things are corrupted. The space, right? Needle, NEEDLE. This is essentially a splitting, right? Tokenization. Only the subject is corrupted, not the other parts are corrupted. Now, why the subject is corrupted? I'll tell you why later. But the output that you obtain from this corrupted run is P star R. Okay, the third version of this model is corrupted with restoration run. So clean run, corrupted with restoration run. In corrupted with restoration, what you do? So this part is a clean run, okay, and this is the corrupted run. You see these inputs are corrupted, subjects are corrupted, right? Here what you do, you identify one hidden state in this entire network. Let's say the hidden state that you are interested in is this one, okay, and you replace the corrupted hidden state with the clean hidden state. You see this replacement here, okay? You replace one hidden state, the corrupted hidden state, with the clean hidden state, and the rest of the process follows as usual. So this is called corrupted with restoration run. If you do this, you again measure the output probability, and this output probability is called this one. This is corrupted with restoration output, right? What is the corrupted with restoration output of returning Seattle? So what is the hope? The hope is that this will be better than corrupted version, lesser than clean, but the better than corrupted version. Clear? And they did this for all the hidden states in isolation, one by one. Think about it. Think about the amount of resources. Do you have this? I don't have this kind of resources. So for all layers, for all hidden states, this is replace this the hidden states with the clean hidden state. What? Okay. And what they measured two things. The first one is called total effect. Total effect is the probability of the clean run and the probability of the corrupted run. Okay. So probability of returning R for the clean persists for the corrupted. And the other one is the indirect effect, total effect and indirect effect. We are mostly interested in indirect effect. What is indirect effect? Indirect effect is the difference between the corrupted one and the corrupted with restoration one. Corrupted and the corrupted with restoration. So higher the difference, what does it mean? Let's say you restore a hidden state for which this difference is high. That means what? That means that hidden state is important, right? So then what they do, they basically do this thing for all the hidden states in the network, and then they plotted this one. So in this plot, you see, this is kind of a some sort of scatter plot, right? Where x-axis indicates the layers, and this is GPT-2 XL. Okay, layer 0, layer 1, layer 2, ... layer 40, right? And what is y-axis? Y-axis is the inputs, right? The space, needle, data, right? And every element in this matrix indicates what? This is the indirect effect, the difference after restoration, right? Every element in this matrix indicates this corrupted, probability of corrupted after restoration minus probability of corrupted. So you see very interesting patterns actually emerged. Now darker the color in this matrix, higher the value of this difference. That means so higher the value of the difference, more important those restorations are, right? So they saw two important regions. So this is one region which is dark. This region is important. When they restored neurons in this region, they saw a change, and this region is also important. They call this region early site, right? Now so this is early site and this is late site. What is late site? So this is late site because this region corresponds to the last few layers. Look at this one. This region corresponds to last few layers, right? And the last token, right? So this late site corresponds to this part, isn't it? Right? Now this is obvious that this part is important because this part is going to return the actual output. So late site observation corresponding to late site is not surprising. This is obvious. But what is interesting is early site. Why suddenly early site? Earlier layer, or essentially middle layer. You see the region layer 10 to 30. Here you see some sort of peak. And another interesting observation is that this region corresponds to the last token of the subject. They did not see any peak here. They did not see any peak here. They saw a peak here, which is the last token of the subject. The subject is the space needle, and this is consistent across other prompts, right? Why is this so? What they did, they further bifurcated this figure. So two components are important here. One component is attention, other component is multilayer perceptron. These two guys are playing important roles. So the way they restored hidden states, similar way they restored the multilayer perceptron, MLP, copied it from the clean version to the corrupted part. Similarly, they copied attention from clean version to the corrupted part. And they observed that for multilayer perceptron restoration, when they restored MLP, right, this early site was very prominent here, not the late site. Whereas when they restored attention, late site is prominent, not the early site. Right? What does it mean? It means that this middle layers, multilayer perceptrons are storing knowledge. Right? So they are the whatever culprit or important components. Right? Let's target them. All right. So this is the first observation. Based on this observation, but still it is not very clear. Think about it. When when you restore the hidden state, right, versus when you restore the multi-layer perceptron, this restoration will also have effects in the other layers, right? It is still not very clear what is the amount of effect that the multi-layer perceptron is playing. Now, what is the amount of effect that the attention is playing? To understand this thing more, they came up with another version of corruption with restoration, right? So this is a corrupted with restoration run version 2. And this is a bit difficult to understand. Please focus on this. So in this version, what they did, they first restore. So this is the clean state. Sorry, this is the corrupted state. This is the corrupted diagram, and this is the corrupted with restoration diagram. Okay, you see subjects are corrupted here. Okay, so in this case, what they did, they first identified a location which needs to be corrupted, which needs to be cleaned, right? And they replaced this hidden state with the clean hidden state first, the way we did this earlier. Okay, along with this, to identify the effect of MLP. Okay, to identify the effect of MLP, what they did, now think about it. HL is HL minus 1 plus AL plus ML, right? Residual stream view. Now, this is clean. This is clean because you restored it, right? AL is corrupted. You did not restore. Now, what they did to understand the value of ML, right? They, to the output of this, so this is the output of this MLP. This is the output of the MLP. They replace the output of this MLP with the corrupted output that we obtain from the MLP of the corrupted setting. That means this is also corrupted. But this, remember, this MLP, this corrupted MLP is not affected by this clean HL minus 1. If I did not replace this, what would have happened? This HL minus 1 will also affect ML, right? I want to sever, I want to block this effect. Okay, so clean HL minus 1, corrupted AL and corrupted ML. This AL, remember, this AL will be operated on top of H minus 1. HL minus 1 will be fed to AL, isn't it? So AL will be affected by HL minus 1's clean state. So ideally AL's output will move to ML. Right? I do not want to do that. So what I do, I cut this connection, right? And I restored this ML, M sub L, by the corrupted one. Okay. So in this setting, what I will gain? I will understand the impact of MLP. Right? I will understand the impact of MLP. So this is one setup. Another setup, you do the same thing for attention. So there are 3 setups now. The first setup is only hidden state restoration. The second setup is only, so the second setup is you sever, so this is called severing. You sever the MLP, and the third setup, you sever the attention. Right? Now let's see what happens. Let's focus on this figure. So let's first look at this purple bar graph. So purple bar graph corresponds to single just hidden state representation, hidden state replacement, right? We saw here, and what is y-axis? Y-axis is the indirect effect. That's the same difference. Okay, we saw that when we replace this hidden state, okay, the impact is very high at the initial layers, and the later layers the impact is low. So till this part the impact is high. Look at the purple part only. Okay, to understand which component impacts the most, right? What I do, I first remove the attention part, which is this red bars, and you see the red bars pattern and the purple bars patterns are the same at the initial layer, meaning that at the initial layer attention is not playing any is not playing any role. But when you cut off this MLP, you see a major difference. So look at this purple and the green at the beginning, right? So the green bar is very low. What does it mean? What is this green bar? The green bar is the indirect effect. Indirect effect means corrupted restoration probability minus the corrupted probability. This is low. This is low means what? The corrupted restoration is similar to corrupted version, right? The model tends to basically become the corrupted setup, right? So it means that the first part of the first segment of layers will be important, and MLP plays an important role here. All right, now so we understood that these layers are important. Now let's look at this again, the multi-layer, this MLP layer. I already mentioned MLP layer is basically a key value association, right? Key value associative memory. There are two components, WSC and W projection, right? The output of WSC is here, this is key. This key will be multiplied with projection, and the projection, and then it will output a value, right? And what is my goal here? My goal here is now restore. My goal here is to inject the updated knowledge, right? So the new key is K star and the updated knowledge is V star. The new key is K star and the new value is V star that I want to add to the model. Okay, there is no external memory concept here like grace, right? I will modify the parameter, right? But I will not modify the entire parameter. It's a localized modification. Let's assume that through all this causal tracing, the causal tracing that I discussed, you identified a specific MLP which is responsible. Let's assume that, although this is a very exhaustive approach, you have to do this thing for all the neurons, but let's assume that you identified a certain MLP which is responsible for this, right? And what you want to change only that MLP's parameters. Okay, so the MLP is this W parameter is W, right? So you pose it as a least square problem, right? Very simple. You have the set of keys K, you have the set of and you have the parameter W. This is MLP's parameter W, right? This multiplication will produce the value V. This is your original V, and you want to minimize this gap. This is a simple Frobenius kind of norm, right? What is the constraint here? The constraint here is for only that edit that I want to make, K star, V star, for those edits, the updated parameter W hat will return the updated value V. There are many other keys, K1, K2, K3, V1, V2, V3. For those, I don't want to edit anything. I only want to return the updated values for the updated keys. So I want to modify W. Earlier this is W. Now the updated parameter of MLP is W cap, W hat, and I want to minimize this subject to this. So if you read the paper, they said, and the derivation is pretty easy, it's not very difficult in the appendix. They said that this objective has a closed form solution, and this is the closed form solution. So what is W? Let me just interpret this. I will not discuss the proof, right? So W is the original MLP layer parameters. W hat is the modified MLP layer parameter, right? So this is lambda. What is this lambda? This lambda is Lagrange multiplier. Look at this. So this is a constant optimization problem, right? You have to do this Lagrange multiplication, right? Lagrange multiplier. What is C inverse? C is basically K transpose. What is K? K is the K matrix, the key matrix. So K transpose is a symmetric matrix, right? And what is this K star? K star is a new key that you want to include, right? It has a closed form solution. This is very nice. It means that you don't need to do this iteratively. And this Lagrange multiplier is defined as follows. The proof is very simple. Go back and read the paper. You'll understand. But what is important here is that this objective function can only be executed if you know K star and V star. Obviously, right? If you know K star and V star, then only you can execute this, right? What is K star? What is V star? Tell me. K star is the new or updated key. Or what is V? V is the updated value. They are vectors. They are not English readable prompts, right? So how do we get K star? Let's say the knowledge that you are interested in to include is that prompt. The space needle is located. Blah blah blah. Right? So the hope is that this key, right? Key will capture the subject of the prompt. The subject is the space needle. So what they did some sort of approximation here to measure. This is again a bit difficult to understand. Please focus on this. So we are interested in this K star. So the subject is the space needle. Okay. So what I do, I will sample many such prompts where the subject is the space needle. I will sample n number of such prompts where the subject is the space needle. Okay. And each of these prompts will be given to the to the transformer, right? It will process till the layer that I am interested in, right? And it will return for each of the prompts. I will get some K, right? And I repeat this thing n number of times for n number of prompts, right? And this is the average representation of the subject, the space needle. What is Kj plus S? So remember, I already found that the last token of the subject is important. So Kj plus S is the last token of the prompt Kj, Xj plus S. Right? I am not interested in the other tokens. I am only interested in the last token of the subject. Right? This is just an approximation. I do this thing n number of times, and then I will get this this key. Now remember, the key is the output of the first layer of the MLP. I am repeating this thing. It is the first output of the first layer of the MLP. Okay? How do we get the value? How do you get the value? To obtain the value, so what is value? So this K star, which I already got just now, this K star will be multiplied with what? Multiplied with W projection. W projection is the second layer of MLP, and that will return you the V, right? Now I am interested in obtaining such a V which will produce the output Joe Biden, right? I am interested in obtaining such a V which will produce the desired output. So my desired output is O star. Okay, and this is my input prompt. So I will measure the probability of this updated desired output, right? And I am interested in such a V, which is Z in this case, right? I am interested in such a V for which the output is O star. So I measure the loss, I backpropagate, and I update the value of, I keep on updating the value of V. It's basically a fine tuning. So, but it may happen that in order to do this fine tuning, I already mentioned that this is a problem of fine tuning. So this is kind of fine tuning, right? Because you want the desired output to be produced by the model, right? And depending on that loss, you will produce the value of V, the value of the representation of V, right? If you want to do this thing again and again, you will be deviated from the original model, and you don't want to do that. Similar to DPO, you don't want to do that. Therefore, there is another component which will tell the model, don't move far away from me. Okay, so the scale divergence is between the original model G and the updated model G. This, right? There are two components here. One is the fine tuning part to obtain the V, and the second component of this loss will make sure that the updated model is not very far from the original model. All right. So now we are done with K star and V star, right? When we are done with K star and V star, I can run this optimization, right? I know this closed form solution. I know this closed form solution here. So look at the components. I know W, I know K star, I know C, I know V star. So V hat can be produced. Okay, this is ROM. So output is as usual. This was published, therefore it has already outperformed all the other baselines. You see full fine tuning. What is KE? KE is the knowledge edit that we discussed, right? Then MENT is another paper, ROM, right? And they perform this with GPT-2 XL and GPT-J with different accuracy measures. Okay, these accuracy measures are essentially a combination of specialization, generalization, localization that we discussed earlier, right? They also measure the fluency and consistency of the output, whether the output is grammatically consistent, fluent or not. That's all about ROM. Okay, thank you.